Hello and welcome to our third lecture in chemistry, the first lecture being the intro, the second lecture being a quick review. And in this lecture, I hope to accomplish a sense of aqueous reactions, just discuss them a little bit in depth. Well, not too much depth. First, we begin by a definition of an electrolyte. An electrolyte, by definition, I'm going to write this on the board. You might want to take notes as you're learning these lectures. An electrolyte is any substance that dissolves in water. And I'm going to omit the preposition that. And as you know, H2O is dihydrogen monoxide, which is water. So now let's think about it. What is it? What is? Let's give us some examples of electrolytes. Stuff that dissolves in water. Well, we know table salt dissolves in water, right? Salt water. What is the equation for table salt? Well, I know it has Na, and I know it has Cl, and I know the charge of Na is plus, and I know the charge of Cl is minus. So then, by that definition, we get that NaCl is a compound that dissolves in water. And we can extend this definition to say that any ionic compound at all will dissolve in water. So KCl will dissolve in water. Let's see another one. MgO2. MgO rather, because Mg is what? Mg is 2 plus and O is 2 minus. So let's write these charges again. 1 plus, 2 plus, 3 plus, 4 plus, or 4 minus, 4 plus or 4 minus, 3 minus, 2 minus, 1 minus, and 0. Because they're happy campers. But, so MgO, any ionic compound. So any ionic compound is an electrolyte. That's what any ionic compound. Now, I'm going to give another example of something that's not an ionic compound yet still is an electrolyte. We have glucose, which the definition is C6H12O6. Glucose, well, this is also a definition of glucose, sucrose, all these sugars. These are called sugars, carbohydrates. I don't know if you actually do know that, but in case you don't, these are sugars, which are basically stuff like your table sugar. Well, it's not technically your table sugar, but it can become your table sugar. But we're not going to worry about that. Just know that ionic glucose and sucrose, all these dextrose, all these sugars are also electrolytes. Now, but these aren't ionic compounds, which leads me to my next point, discussing about weak versus strong. Weak versus strong. The difference is whether a compound, I'm going to abbreviate, a compound will dissociate completely. Now, we need to decide whether a compound, when you put it in water, is going to completely dissolve and dissociate, or just dissolve and not dissociate completely. And a good example for that is acetic H2C2H3O2. Believe I did that right. I'll probably just change the description if I did it wrong. But acetic acid this is called acetic acid. Note that to name an acid, all you do, well, we're going to discuss acids, but all you do is you take the compound, which is acetate, and then if it's 8, you drop the 8 and add ic, acetic acid. So that's the naming of that, but we're going to get into that in a little bit. However, this does not actually completely dissociate in water. It'll dissolve. It'll break up into H plus ions. It'll yield H plus ions, and it'll also yield C2H3O2 minus ions, acetate ions. But it won't do so entirely, and the nature of that is because they're weak. They're weak versus strong electrolytes. Now, versus NaCl, which will yield Na plus, well, we're going to put actually Na plus and Cl minus. It'll completely dissolve, and the reason for that is, well, the reason is that this is a weak acid, versus this is a very strong ionic compound, which will break up as soon as it sees the water. It'll get excited, and it'll break up into Na plus and Cl minus ions. But these won't exist by themselves, so we have to put a little subscript. Let's say this was solid, and let's say this was in a solid form as well. We had a powder of acetic acid powder, and we had, the table salt that we're going to sprinkle into water. So we drop it into water, and then what happens is we put aqueous for these because they're dissolved in water. And the reason they're aqueous is because this Na plus ion is going to be attracted to one of the H's. I'm not going to draw a bond. I'm going to draw a little dot to one of the H's of the hydrogen of the water, versus the Cl ion, which will be kind of attracted to the Cl of there. So yeah, these won't break up entirely, and this won't break up these won't break up entirely. Well, in our solution, we'll have kind of the ions existing as both. We'll have the situation existing as both acetic acid as well as these, and that's what you call a weak electrolyte. If something is a weak electrolyte, it doesn't dissociate. It doesn't dissociate completely. So then what we do is, since it doesn't dissociate completely, some ions are going to stay as acetic acid, and some are going to go to hydrogen plus ions and acetate, pure acetate, not even in a compound. So what we're going to want to do now is we're going to want to say that it is an equilibrium, meaning that it exists in both forms. After you drop it in, eventually it's going to get to a state where there's an equal number of acetic acid particles, as well as H plus and C2H3O2 minus particles. So this symbol right here means equilibrium, which means that after we dump it, we allow it to settle and run its course until it kind of calms down, and then we take a look, and it's an equilibrium, which means it's going to be equal parts of both the reactants, as well as equal parts of the product. Versus this is a strong electrolyte. I didn't draw that perfectly, but this is a strong electrolyte. So we're only going to have, I'm going to redraw this, we're only going to have it yielding Na plus ions and Cl minus ions. We're not going to see any NaCl in there. Of course, if we're in perfectly normal standards, if it's very, very small, then the NaCl has to exist, because then it can't roam around. But otherwise, it's going to be very compact. So that is electrolytes. Dissolution, ability to dissolve. If it does dissolve, then it's an electrolyte. If it does dissolve, it's an electrolyte. But if it dissociates completely, then it's a strong electrolyte. And if it's weak, then we're gonna kind of go off here, and we're gonna say it's a weak electrolyte. An electrolyte meaning solely just the ion's ability to dissolve and dissociate in an ion, in an aqueous solution. That's what makes an electrolyte. Now, the next topic in aqueous chemistry is to predict reactions based on these solubility rules listed here. It's in your best interest to memorize these, because they're very, very important, and on an AP test, they're not going to give them to you. However, your teacher may see fit to give you a solubility table, solely because there's a lot of information on here. And I also have set up a periodic table. So what an aqueous reaction is when you have two compounds, and I'm just drawing on a periodic table to give me some space. So when you have two compounds, so let's say I had PB, Cl. Let me draw that again. Let's not do PB actually. Let's make it simpler than that. Oh, let me go for my eraser. Let's make it something simpler than that. Let's go for Mg SO4. SO4 2 minus, Mg2 plus, we balanced that out. And let's say that's aqueous. Let's say we drop the MgSO4 powder into water, and it dissolves. Because why? This is an ionic compound. It's obviously an electrolyte. It's going to be a strong electrolyte as well, because MgSO4 is an ionic compound, and ionic compounds are very strong electrolytes. And let's say we have an aqueous reaction of this, and we also have an aqueous reaction of, let me think. Okay, let me do HCl, hydrochloric acid. We drop that powder into water, so it's aqueous now. And let's say we wanted to see what this compound yields. Well, if it's going to yield anything, it's going to create something that's insoluble in water, something that is not an electrolyte. And to do this, we got to just check and see. These are dissolvable, but when they change, when they move over, does anything become indissolvable, undissolvable, not an electrolyte, a non-electrolyte? Well, the only way it could happen is if we just switch them, because these are obviously the case. So let's try something. Let's bring the Cl and Mg. Let's do a double displacement reaction. You might remember that from chemistry as being when you just simply swap the two compounds, swap the two atoms in the opposite in the two reactants. Sorry, I have to be very precise when I'm talking chemistry. You have to be very precise. MgCl2, because Cl minus, Mg2 plus, change the charges, MgCl2 plus, well, it's going to be HSO4. But have you balanced it? No, SO4 2 minus. Ensure that you have that. And I'm not going to bother right yet balancing this equation. Obviously, we're going to have to balance it because there's 2 chlorines and 2 hydrogens. All we have to do now is just put a 2 in front of that baby. And we have 1 Mg, 1 SO4, 2 H's, and 2 Cl's. But let's see what happens. Let's see if any of these compounds are insoluble in water, which means they net a non-electrolyte. And because they net a non-electrolyte, they are insoluble in water, and the reaction happens. Well, we have Cl right here in this solubility chart, and it says all chlorides, bromides, and iodides, which are also known as, halides. And halides are, if you remember from last year in chemistry, or chemistry 1, I have a periodic table right here. I don't know why I switched that. These are called the halides. Halogens, halides. Halides is their ionic form, is their ion form, and their halogens are when they're in a pure state. And these are known as the halogens because they're -1 charge, all there right there, and they're really close to being noble gases. You learned a lot about halides, and you're gonna learn a little bit about them in this course as well. So if all the halides are soluble, and then they have the exceptions right here: Ag silver plus, Pb plus, and Hg2 plus. And PbCl2 is slightly soluble in cold water and moderately soluble in hot water. Well, are we dealing with any of those compounds? No, we're only dealing with Mg. So because Mg is not on here, we know that this is not the resultant compound is going to be an electrolyte. And is it going to be a strong or weak electrolyte? I'm going to guess that it's going to be a strong electrolyte. And therefore, we know that this is also going to be aqueous. It's going to dissolve. Even if we hypothetically were to take MgCl2 and take a powder and throw it into water, you know damn well, because of this general solubility rule table, that it's not going to become a solid. It's going to dissolve. It's going to dissociate. I'm pretty sure it's going to dissociate completely, and it's going to dissolve. And because it's going to dissociate completely, it's going to be a strong electrolyte. Versus if it did not and it maintained equilibrium. So let's do this hypothetically. It's very important that we go back and we really review what equilibrium means. If this would be equilibrium. This is the equilibrium sign. Instead of a reactant, meaning it's going to go solely there and not going to go back. So we're going to go solely there and not go back. An equilibrium sign means that it's going to go back and forth. That would mean that it's going to have Mg2 plus ions and then Cl minus ions. But would this be balanced? No, there's 2, so we have to put 2 there. And that's the reason why we wanted to do this, to show you guys that sometimes you have to put coefficients in front of the Cl. And now let's take a look at this. So this would not happen. It's not going to be. I'm pretty sure it's a strong electrolyte. I'm probably going to correct it in case I'm wrong, but that's that. So we've predicted that MgCl2 is going to be aqueous, but what about SO4? Well, we look at the solubility rules. SO4. All sulfates are soluble except for those of barium, lead 2 plus, and calcium, and strontium. I think strontium is the... Yep, strontium. Yep. And H2SO4, well, hydrogen is not listed on there, so obviously that's going to be aqueous as well. So does a reaction really happen? Think about it. We have something that we can't even see. We have water in here, and good thing I'm using blue, we have water, but it doesn't really look like there's any powders or anything in it. It kind of just looks like water. And then we have another beaker of hydrochloric acid, or HCl, which is hydrochloric acid, and it's probably one of the, you don't want to touch this. You don't want to touch this inside. You don't want to put your finger inside there. But let's say that we have these two, and then we're gonna just combine them. We're gonna dump one. Let me see if I can do this. I'm gonna dump one. Nope. Let me take this back. Let me group this. Oh, nope. I didn't mean to do that. Let's group this. See if I can just take this. Whatever. Let's say I want to take this beaker and I'm going to dump it. I'm going to dump this beaker right inside of there. And then what happens? Well, in that resultant reaction, it's really not going to look much different. I mean, the reactants are also aqueous, so there's no reaction. So basically, you're just gonna have all the ions floating around, and they're all gonna be so happy and so content with the H2O molecules that they're not gonna try to bond with them with the other atoms. So therefore, we don't even have a reaction. And now let's think of a reaction. Let's say I have. Let's say I have sulfuric acid, and let's say I had BaCl minus, BaCl ion, BaCl2 rather, because it's barium. Barium's a 2+ ion. How did I know that? How did I know barium's a 2+ ion? Because barium is right here in the 2+ column, and Cl's a -1 column. So we're gonna balance out by just 2+ goes over here, 1+ goes over there. That's BaCl2 plus H2SO4 aqueous. And is BaCl2 aqueous? Yes it is. BaCl2 is also aqueous. So then we're going to dump these in there, and obviously as we did in the previous reaction, we're just going to have to move them around. So BaSO4. And that's all. Barium sulfate. There's no 2, there's no 1, there's none of that. Plus HCl. Now, this is also going to be a 2 right here. We're going to put a 2 right there to balance this out, because 2 chlorine, 2, everything else works out. HCl, well, we already know that's aqueous, but let's just check it again. Cl, yeah, there's nothing that's saying that it's not aqueous, so we're going to put aqueous. But what about BaSO4? SO4, all sulfates are soluble except for those of Ba2+. But that's what we had. We had Ba2+ right here. So then we have a solid, meaning it's going to look cloudy. It's going to look white. It's not going to look clear anymore, because the ions are going to collect, and they're going to be like, no, I'd rather be with barium's going to say, I'd rather be with sulfate, and sulfate's going to be like, I want to be with you, barium, as well. They're not going to say, oh, I want to continue with the water. They're going to find a better attraction between the two molecules. And when this happens, when there's a solid that's formed from the reaction, from an aqueous reaction, we call this a precipitate. Precipitate. It's a fancy term, but all it means is it's a solid. There's a solid that's formed. That's called a precipitate. Let's see if we can use our recognize precipitaph. Good enough. It's called a precipitate, guys. And so that's predicting. Now we got to come up with a net ionic equation, and let's just use this. Let me delete this. This is called a precipitate. You guys all know that. Now, let's say we have to, and this is a solid. Let's say we have to write a net ionic equation. A net ionic equation is basically saying, when we have spectator ions, which are spectator ions, we write that. We have precipitate. That's one term. Recall what that means. And then we have something called spectator ions. And spectator ions are ions that do not take part in a reaction. Now let me see if I can turn this one. Let me see if I wrote that a little bit better. Recognize. See if it says recognize handwriting. Ions. Oh, Johns that do not take part in a reaction. Good enough. Now, in this reaction, all that's happening is BaCl2 is getting turned into BaSO4. H and Cl we're going to remain as H plus and Cl minus ions in the solution. So all we need to write is that if anytime you have barium in one and sulfate in another, then you're going to come up with a barium in one and sulfate in the other. You're going to come up with a precipitate. So let's go over here. Let's copy all this. Let's move this down here, and let's get cracking. Oh, it didn't. It moved it up there. Let's see if I can. Nope. See if I can just kind of highlight this and then move on. There we go. That's what I'm talking about. But SO4 2 minus SO4 SO4. Nah, whatever. Screw it. Let me just rewrite this equation. Our equation was H2SO4 plus BaCl2 yields BaSO4 plus HCl, and there was a 2 in front of there to balance that out. And this is solid. This is aqueous. This was aqueous. This is solid, and this is aqueous. And how did I get that? I just kind of copied that down there. Now, let's expand this aqueous reaction. Instead of writing aqueous, let's actually write out what's happening. Well, we have two H plus ions floating around, H2, but H2 aqueous, that means that all the ions have dissociated. Remember that dissociation that I wrote up there? Remember that? That's down here as well. Oh, my phone's ringing. We're going to ignore that. And now we have plus SO4 aqueous. Nope, let's not write aqueous. I'm sorry. We're going to worry about that later. And we're going to say that SO4, and what's the charge of SO4, guys? It is 2 minus, or minus 2, 2 minus, whatever it is. We're going to say plus Ba. Ba is just floating around as a 2 plus ion. And then Cl, 2 Cls, because Cl2, 2 Cls are floating around as a Cl minus ion. And then we're going to yield, well, we're still going to have 2 H plus ions rolling around. And we're still going to have 2 Cl minus ions rolling around. But now we're going to have a big clump of BaSO4 rolling around. BaSO4. So let's write all these. This is aqueous. All these are all aqueous. All these are aqueous. But this is solid. So if we see something on the left and the right side, we're going to cross it out. So we see that. Do we see SO4 2 minus? No, we do not. Do we see barium? No, we do not. Do we see 2 Cl minus? Yes, we do. We can cross that out. So what have we crossed? What have we crossed out? We've crossed out the spectator ions. Let me write that. That's another term. Spectator ions. Ions that do not take part in a reaction. So now this is a complete ionic equation. When we have all the ions listed out before we've crossed them out, of course, that's a complete ionic equation. Let's also put that term down. Complete ionic equation. But later on, when we have to just condense this down, so what we're left with, let me rewrite this in a little bit cleaner fashion. I'm just going to move the Ba2 plus because of commutative property. Yay, math. SO4 2 minus, and this is also aqueous, yield BaSO4 solid. And this is what you call a net ionic equation. We just derived a net ionic equation. What did we do? We took all the ions that were spectators and we basically removed them from the picture. And then we got a net ionic equation. And this says that anytime we have Ba2 plus ions and we have BaSO4 2 minus ions, no matter what the other compounds are, I mean, no matter what the other atoms are, we could have Ba phosphorus for all we care, and we could have I don't know, calcium sulfate. But no matter what we have, we're always going to get BaSO4. That's a net ionic equation. And why does it happen? Because of the solubility rules. And you could technically do this with a lot, but I'm just going to do one because I just want to move quickly through all these. Now, let's talk about acids and bases. Very simply put, acids have an H in front of them. Bases have an OH after them. Acids usually occur with nonmetals. Bases usually occur with metals. That's very simply put. So let me draw one. Is this an ion? Is this an acid? Or is this an ion? Is this a base? This is an acid. Is this an acid? Or is this a base? This is a base. Why? OH. That's basically all it is. I can't think of anything else. Now, weak acids and strong acids. I'm going to list a couple strong acids. You basically need to know them. I guess I'm going to go ahead right now and I'm going to draw out, I'm going to label, I'm going to pull this out, I'm going to write all these strong acids out. And these are just acids that are strong. And we're going to make a correlation between acids and electrolytes in a second. Let me write down all these. I want to make sure that I'm giving you guys the right information. So, strong acids. I'm going to list them right now. Strong acids are strong electrolytes, but we're going to first just know them. So, strong acids. And let me change my color. I'm going to change this color to red. And strong acids are going to be HCl, HNO3, that's nitric acid. This is hydrochloric acid. And if you don't know how to name acids, very simply put, if this is a monatomic ion attached to the hydrogen, monatomic meaning only one and ion meaning minus, then we put hydro and then the name of the element. So hydroiodonic, hydrobromic, hydrosulfuric, so on and so forth. And we add ic, not ate. We add ic, not is. And for these, this is nitrate, right? So again, nitric acid. That's hydronitric acid. That's hydronitric acid. This is hot nitric acid because it's nitrate. It's a polyatomic ion. So with polyatomic ions, you don't put hydro or anything in front of it. And right here, H2SO4. H2SO4. This is called sulfuric acid because H2SO3. It has sulfite. Ite becomes us. So sulfurous acid. That's not a weak acid. That's not a strong acid. This is a strong acid. So we have 1, 2. We have these are very common strong acids. I'm sure these aren't the only ones in existence, but these are the ones that we look at. Next we have HClO3, which is chlorous acid, because ClO4, which is the next one, is chloric acid. O4 is chloric acid. Because this is chlorite, it becomes chlorous acid and chloric acid. Next, we have number 6, which is going to be hydrobromic acid. Monatomic, remember, so we do hydrobromic acid. And what do you think this is going to be called? That's going to be called hydroiodonic acid. And all I can really tell you is that you're going to have to memorize these. So note that nitrate, sulfate, chlorate, chlorite, and then all the halides except for HF, all the halides, and then the 2 chlorate and chlorite, and then the 2 nitrates, and then we'll be good. And those are all your strong acids. The best way is going to be to memorize them. There's no other way to kind of you can think of a mnemonic way of memorizing them, but I can't think of anything. So now, strong bases. Your strong bases are going to be the BA. I'm going to write strong bases, and these are going to be your BA, CA, and SR hydroxides. These are going to be, so in other words, let's say BaOH2, CaOH2, and then SrOH2. These are all strong bases. Now I'm gonna write something. Could be kind of correlation to sum this one up. If something's a strong acid, then it's a strong electrolyte, meaning it dissociates completely. And if something's a weak base, it means it's a weak electrolyte, and it's this weak electrolyte, and this exists. Also, let's put for strong bases are also strong electrolytes, and weak acids are also weak electrolytes. I just wanted to put base in there so you guys know that either or works. So remember that either or. Let's put either or works. I'm gonna try to draw that really quickly. Now, a neutralization reaction is very simply put when an acid and a base, which we've previously discussed, just come together. So let's say let me pick a strong acid. Let's do HClO4, chloric acid. Perchloric acid. Notice what just happened there, guys? I made a mistake. This should be chloric acid. I made a mistake. See, this happens to the best of us. And this is perchloric acid. Perchloric acid and chloric acid. Anyways, now that we have chloric acid, and let's pick up a strong base, BaOH2. So perchloric acid and barium hydroxide. And basically what's going to happen is the acids and the base part and the acid, the hydroxide and the hydrogen are going to create water. This is, and then these two salts are going to form together to form an ionic compound. And because Ba is 2 and ClO4 is minus, we get that it's going to be BaClO4 2. ClO4 2, Ba 2. So that means we have to put a 2 right there, and I think we're balanced. No, we're not. We have to balance this equation further out. So we get, let me rewrite this then. So we know what what happens when we get an acid plus a base, we get the salts, BaClO4 2, and then we create water. But let's try to see if we can balance this. Well, we have Ba, and see if you can try to do it before I can. I'm very slow at balancing, I will admit that. And we have H is an O, and O8, and O's. We have to put it as O's. So that's 1. Let me see if I can just do this without that, though. We have 2, we have 8 here, so we have to get 2. Okay, I'm sorry for the cut there, but just bear in mind that if you were to properly solve out this properly balance it, then you just get a neutralization reaction. That's all that is. And then lastly, we're going to work with redox reactions. And redox basically stands for reduction and oxidation. And you want to think of redox and oxidation in terms of charge. So let's create a reaction. Let's say we have methane, which is CH4 gas, reacts with O2, which is a gas, to create what? Well, this is a combustion reaction, right? This is oxygen reacting with methane. So all that's going to happen is carbon dioxide, which is a gas, and water is going to be produced. And I'm pretty sure it's a gas as well. Now let's balance this. C, that's right, H4. Oh, we got to put a 2 there. And if we put a 2 there, everything works out because that's 4 and then that's 2. Yeah. So CH4 plus O2 yields CO2 gas plus 2H2O. And now we have to try to figure out about oxidation and reduction. Well, let's think about this. What is the charge of this carbon molecule? We know that it's plus 4. And what is the charge of this hydrogen molecule? Well, each of the 4 hydrogen molecules has a charge of -1. So basically we have -4 hydrogens, each with a charge of -1. Same with oxygen. What is the charge of the oxygens? Well, each of the oxygens has a charge of let's think about this. Redox reactions deals off the fact that a certain atom will want to get a certain number of electrons, right? That's the whole point of charge, right? Hydrogen just needs to lose 1 electron. It's good. Carbon just needs to gain 4 electrons, and it has the ideal 8 wholly number. So that's the same exact thing with redox reactions. But right here, oxygen's pretty happy, and there's no reason to say that one oxygen has any charge over the other. So we're going to put a 0 right here. Next, we have plus 4 again, and each of these oxygens has a what? A 2- charge, right? That balances out. That's happy. And now this H2, each of these H2s have plus 1, and this oxygen just has a -2, and everything balances out. Now, let's write some reactions to see what happens with each of these molecules. C plus 4 is going to yield what? C plus 4. So what is the change of electrons there? There's no change of electrons with carbon. It neither got oxidized nor reduced, so it's neither an oxidizing or reducing agent. What is oxidation or reduction? That means that the charge of something is going to go up, which is an oxidation. The charge of something is going to go up, or reduction. The charge is going to go down. Reduce goes down. Oxidate means go up. Now, next, so we're going to have to say 0 electrons, so don't worry about that. Next up, let's look at hydrogen. Does hydrogen have any change? Well, let's see what happens. We have 4H minus 1 charges. 4H minus 1s yield what? 4H plus 1s. So what happened here was we went from 4H minus 1s to 4H plus 1s. So the charge went from -1 to +1. So was that a positive change or a negative change? Well, it went from negative to positive, so that's a positive change. So that means since the charge went up, it's oxidized. So we added 2 electrons. And doing that, we got +1. That was good. So that means this was oxidized. This is an example of oxidation. And next we have oxygen. So we have to worry about oxygen. So let's see here. We had 2 O's with the 0 charge, and then that yielded 2 O's with a what charge? 2 O's with a -2 charge. 2 minus charge, -2 charge. Or 2 plus 2. It doesn't really matter. But let's see what happened. Well, we went from having 0 to having -2. So obviously we got rid of 2 electrons. So oxygen was reduced. But by what? Well, the 2 electrons here went to here. So reduced by the hydrogen and oxidized by the oxygen. So if something's reduced by something, that means that oxygen is the oxidizing agent, which means that it was the one that did the oxidizing of the hydrogen. Makes sense, right? We named oxidation partly after oxygen. Next, we have hydrogen. Hydrogenizing agent. Hydrogen was gained electrons, and it was oxidized by O and reduced by. So oxygen was the reducing agent. It is the one that reduced oxygen's electronic charge. And that gets me to the end of today's lecture.